Hello everyone, welcome to this presentation where I will be spending the next 15 minutes talking to you about a resonant gate driver with variable gain and a capacitively decoupled high-side GaN-FET. I'm going to spend one or two slides talking about previous work in this area before introducing the proposed driver topology and discussing some practical considerations which need deliberation. Then I will demonstrate a discrete prototype and show some preliminary results before concluding this talk. So on this slide, I'm showing a selection of previous work. The three on the left I would describe generally as lower frequency, more mechanistic methods in which an inductor is used to steer current into and out of the switching devices with high efficiency. Typically, these control schemes require a number of switches and are often a little bit more complicated, with some requiring advanced knowledge of a switching event such that the inductor current can be ramped up to a specific value before turning the device on and off with high speed. Conversely, the two gate drivers on the right fall into the category of what I would call tuned resonant methods, whereby the gate driving voltage waveform is of a fixed frequency and duty cycle as dictated by surrounding component values. This allows one to operate at much higher frequencies, generally speaking, where you are somewhat immune to clock jitter or timing errors because its operation is somewhat automatic. Some of these approaches enable voltage swings that extend beyond the rails of the power supply provided to the gate driver. So this allows for low voltage, high speed driving devices to be used in higher voltage driving applications, such as silicon carbide, where you could potentially use a 5-volt supply to drive a gate voltage of, say, plus 15 volts to minus 5 volts, for example. The topology I'm about to present to you aims to sit somewhere in between both of these areas and thereby retain the versatility of the lower frequency guys on the left with respect to having a variable frequency and duty cycle, but while also retaining minimal timing requirements such that it can achieve higher frequencies effectively, in addition to gate drive voltage amplification. To arrive at this gate driver, first of all, we start off taking a look at a conventional low impedance pull-up, pull-down driver. So here we've got unmitigated CV²F loss, whereby we lose half of our energy in charging up the input capacitance, and we dump out the remainder into ground once we're done with it. And we do this every single period. So to start changing this into a resonant gate driver in which most of this energy is instead recovered or conserved, we can start by adding an inductor in series with the gate. Now, in this case, if we look at the gate voltage waveform, we see that we have exaggerated or accentuated the gate ringing. And we see that the extent of the ringing, or the percent overshoot, is a function of LC values and parasitic loss elements. So here, instead of burning off our CV² energy in an overdamped manner, we are using it to deliberately boost our gate voltage. The next obvious step is to figure out some way to latch our gate voltage at the maximum voltage it reaches. We could do this using bidirectional switches for S1 and S2, but this would require accurate turn-off timing. And as mentioned, we would like to keep our clocking requirements as simple as possible. So instead, what we can do is add two diodes, which will inherently capture the peaks. And this is one solution that was published quite a few years ago. Now, note that the voltage swing will keep increasing cycle to cycle until parasitic loss limits the gate swing. This approach works quite effectively. However, tying S2 to ground restricts you somewhat in terms of what gate voltages you can swing between. So in this work, what we're going to look at is applying independent pull-up and pull-down voltages, termed here as Vpos and Vneg, which will allow us to independently tune both the positive and negative peak voltages. So to give a little bit more detail, during a rising edge, Vpos delivers charge or energy onto the gate, and during a negative swing, energy is recovered or absorbed by Vneg as D2 conducts. So in this sense, since Vneg is always absorbing energy, you can imagine that energy being used elsewhere or potentially being pumped back up to Vpos via some auxiliary small converter, thereby closing the energy loop. As mentioned, D1 and D2 relax the turn-off timing constraints on S1 and S2, and that's indicated here by the shaded or hatched regions. The switches can turn off at any point during the shaded region without affecting the gate driver's performance. So since the gate swing is entirely dependent on parasitics, we really need to pay attention to which devices we use. Given their minimal parasitic capacitance, in this work we decided to use some small gallium nitride FETs in place of S1 and S2. However, this comes with a set of challenges, as will be discussed next. First of all, M2's source is not connected to ground, but instead connected to VNeg, and so it is inappropriate to use a low-side gate driver as depicted here. Although, since VNeg represents a constant DC offset relative to ground, we can use some straightforward capacitive decoupling to level shift our gate drive signal to M2. In this case, the decoupling capacitance CG2 is significantly larger than the CISS input capacitance of M2. To further ensure that the correct offset is stored across this decoupling capacitor, we can add some small passives or a Zener diode to clamp M2's VGS within the appropriate range. For the high side switch M1, things are a little bit more challenging. Here we cannot use the common bootstrapping approach, which is often used in the conventional half bridge as depicted here on the left. You can see that in our case, the source of M1 is not directly coupled to the drain of M2, and instead we need an alternative approach. So taking inspiration from what we did for the low side switch, we can apply a similar capacitive decoupling technique to the high side switch M1. In this case, we add 2 more decoupling capacitors and some small passives to set an appropriate offset. Unfortunately, a problem still remains. If we take a quick look at the conventional half bridge once more, you can see that all expended charge from M1 is ejected into the primary power flow path. Now in this case, this has been made impossible by the introduction of CS1, and as such we need an alternative path for the charge to be released. And so we add one small additional transistor, M3, whose job it is to periodically release this charge to ground. M3 also acts to ensure that U1 flies definitively between ground and some higher potential, resulting in the conventional bootstrap diode DBT on the left to be used appropriately here. In this case, M3 turns on while the gate driver output is low, or the source of M1 is at its lowest potential. Finally, we can generate an appropriate gate signal for M3 using the propagation delay of the low side gate driver itself. To summarize this gate driver's operation, here we plot several voltage waveforms. Each of the color-coded nets on the schematic corresponds to the color-coded waveform in the plot on the right. We can see that a near constant voltage difference is maintained across the high side bypass capacitance CBP1, with the exception of when M3 turns on during the low output state. This acts to increase the voltage stored on CBP1 and replenish the charge lost when M1 turns on. Similarly, we can see that the source of M1 in red maintains a constant voltage offset relative to the green net, as decoupling capacitors CS1 and CG1 maintain appropriate offsets. If the steady-state waveform of M1's source were to change, say if Vpos or Vneg were adjusted, the DC offset stored across CS1 will track appropriately since the green net is shorted to ground every period. Next, we will take a look at a discrete prototype shown here in the figure on the right alongside a 1200-volt silicon carbide device. Here you can see the air core inductor at the top, below that diodes D1 and D2, the dual gate driver on the left, and EPC's small triple GaN-FET in the center. This tiny BGA part is used to instantiate M1, M2, and M3. The driver's total component volume is a little over 17 millimeters cubed, with 55% of that being the dual gate driver, about 28% being the inductor, and with the GaN-FETs consuming about 8.5%. The rest is made up by small diodes, capacitors, and resistors. The driver was used to control 4 different commercial FETs, one silicon carbide as depicted, and 2 gallium nitride. The FETs were chosen for their low intrinsic gate resistance with respect to their input capacitance, CISS. This property is critical in maximizing the percent overshoot and subsequent resonant gate driver efficiency. Unfortunately for us, in this case, manufacturers often deliberately increase the gate resistance within a power device to improve reliability and immunity to ringing and ESD events in hard charge driver applications. As such, a power FET with a low gate resistance designed explicitly for resonant gate driving schemes would likely further improve this driver's performance. One of two inductors were used for each device tested, either 12 nanohenries or 27 nanohenries, which provided an estimated Q factor of somewhere between 5 and 12 when discounting parasitic losses. This region was chosen to provide a moderate balance between gating loss reduction and increased rise and fall times. Here we show a table of results for the 4 devices tested. The switching frequency was kept somewhere between 10 and a little over 20 MHz, while the rise and fall times resulting from the LC resonant action were between 6 and 18 nanoseconds. The maximum and minimum VGS gate voltages, Vpeak plus and Vpeak minus, were selected by manually adjusting Vpos and Vneg. In the case of the silicon carbide device, Vpos was set equal to VDD at 5 volts, and Vneg was connected to ground, thereby eliminating the need for any additional power supply generation. Given this gate driver's high impedance holding state, in order to avoid the possibility of Miller turn-on, Vpeak minus was selected in all cases to be sufficiently negative as to ensure that the gate remains lower than 0 volts for a drain-to-source increase from 0 volts to 70% of its maximum rating. The expected gate voltage increase due to Miller feed-through was estimated using gate-to-drain capacitance listed in device datasheets. Since this driver's intended use is in soft-switched converters, where reduced rise and fall times are acceptable, the drain-to-source voltage was shorted to ground with no bus voltage applied. Of course, further data acquisition with a time-varying drain-to-source voltage would serve to empirically validate the driver's expected immunity to Miller turn-on. To compare the gating loss of this resonant driver topology to that of a conventional hard-charged gate driver, the inductor and diodes were shorted while Vpos and Vneg were set equal to the previously measured resonant peaks Vpeak plus and Vpeak minus. This effectively converts the driver into a conventional hard-charged half-bridge output stage with the same drive voltages being applied to the device. Since resonant action has been removed, CV²F gating losses are reintroduced. This table at the bottom lists the relative improvement in losses seen by the proposed resonant topology versus the conventional half-bridge output stage. All devices tested saw at least a 52% reduction in total loss. On the right-hand side, we see 2 example VGS waveforms. The top right depicts a GaN-FET switching at 20.5 MHz using a 12 nanohenry inductor. Here we see symmetric oscillations about Vpos and Vneg as expected. Additionally, the lower right figure depicts the measured VGS gate signal with a varying pulse width duration, illustrating this resonant driver's suitability for use in topologies with diverse duty cycle requirements. A gradual VGS settling is also observed here. This effect is due to leakage and the charging of parasitics throughout the driver stage. Since this driver is high impedance while holding, leakage results in a lower bound being placed on switching frequency, further highlighting the importance of non-ideal element considerations. So to conclude, operating at high frequencies of 10 to 20 MHz, the proposed gate driver achieves up to a 72% reduction in gating loss when compared with conventional hard-charging gate drivers, while tolerating moderately increased rise and fall times up to 18 nanoseconds. Using 2 N-channel devices in its output stage, this design benefits from a significant decrease in parasitic loss relative to complementary CMOS output stages and acts to extend the efficacy of this design at higher switching frequencies. While generally used as primary switching elements, here 2 small gallium nitride devices further contribute to the driver's attainable switching frequency through their reduced parasitic capacitance. Since conventional bootstrapping techniques are non-applicable in this design, here we described a capacitive decoupling technique which allows power delivery to the driver of the high-side N-channel device in the driver's output stage. Furthermore, relaxed clocking complexity and a variable frequency and duty cycle give versatility and extend use case applications. Moreover, this driver exhibits gate voltage amplification with both positive and negative peak voltage values being independently tunable through drive voltage adjustments. Future work will include applying the proposed topology to a functional resonant or soft-switched converter. In addition, we have begun work developing the system of equations which define the steady-state operating point, including parasitic contributions, and we intend on demonstrating a complete closed-loop energy recovery system where both positive and negative gate swings are regulated to precise voltage levels. Lastly, we would like to acknowledge the support of Jim Weiser at Texas Instruments and EPC Efficient Power Conversion for donating parts. So thank you for listening, and I would love to hear any of your questions or comments on this design space. Cheers.